smash like that.
Yeah, I need to play for it now. I don't need to play with Jason. It's like, so you don't really.
So I thought you can draw the arrows or solution.
That's all I care about.
That doesn't.
You like plug it, no, it's really, you plug in the line, draw the arrows.
So like, I think we can keep from getting grounded for a bit longer. That one. If you draw it, I don't.
Okay, let me just go over the calendar here. The calendar is on the inside page of your, on the other side of your cover. Really, there's only 3 major topics that we're going to go over. So this unit, we're going to just have a quiz over this unit, solving differential equations, and then working a little bit with population growth equations, and then we'll do slope fields, and then we're going to start reviewing for our third. So it'll be a basically solving differential equations will feel like what we did with U substitution. It's just that now we're working with both sides of the equation, and so it's just going to extend the problem a little bit longer than before. After this, we're going to start our final unit of this semester, which is area volume. And typically students find these topics to be a little bit easier because it's just the setup. If you can do the setup, the rest of the work can just be plugged into the calculator. So we will cover those sections, but we're not going to have and then this unit is also a quiz, but we're not going to have a quiz until after we come back from break. So after we come back from break, we'll do some more review. We'll have a quiz, and then I'm going to have a test over certain FRQ topics, but we'll have 2 weeks to prepare for it, so we should be fine. Okay. And some of it will be very similar to the one that you're going to see on Thursday. So a lot of it will just feel familiar. But I wanted to kind of end this semester with AB topic FRQs, so that we can kind of end our AB content unit and then start our BC content in January. Okay, but hopefully we'll still have time to review some of the FRQs that you're going to see on Thursday. So again, it will be a derivative graph, a Riemann sums, and a particle motion. Okay, so let's go to page 1. Oh, and there's something else that I did with packets is that I think it's easier for students to find their homework if they're all grouped together. So I put all the AP practice at the end of the packet so that you won't have to flip through a ton of pages just to get to your homework to show me. So 7.1 to 7.3, and your homework would just be the AP practice, okay, in this packet. And whenever we don't finish with the notes, I'll specify. Okay, so page 1 here, differential equations. Okay, so differential equations, basically that just means a derivative equation. Okay, differential equation is just equation at the derivative level, or derivative equation. And when we talk about solving a differential equation, all that means is that we are taking the derivative, taking the antiderivative, and bringing the derivative up to the function level. That's all it is, right? And we've been doing that ever since we involved or introduced first theorem calculus. But now we may have things that are that need some rearranging before we can take the antiderivative. So the first thing we need to do is something called separation of variables. We need to rearrange equations so that our dependent variables are together, which is our y and dy usually. Those are the variables usually for dependent variables. And then the x and dx are your independent variables. You want to group that on the other side of the equation. All right. So here, solve the differential equation dy dx, dy over dx equals 2x over y. So what I like to do, and right now, if you can just follow the pattern that I have set, and then if you want to, if you choose to go down another path, or if you choose not to go through all these setups that I do, that's fine. But I think for now, it's nice to kind of have some basic structure. It'll be easier for me to present it. So the way that I like to start the process is I like to cross multiply. So the nice thing about cross multiplying, it may not separate your variables, but it will get your dy dx's in the right places. Okay, kind of gives you an anchor to begin with. So that's always my first step. I'm going to just always cross multiply. In this case, I'm going to cross multiply in a way where my dy is going to be on the left and dx is going to be on the right. One thing that we need to make sure that we do is that your dy dx's have to be in the numerator. Okay, if your dy dx's land in the denominator, we don't have the correct setup. It's okay to have y's and x's in the denominator, but we definitely need the dy dx's up top. But here, after I cross multiplied, everything's already in the right places. The y's are together, the x's are together, the dy is up in the numerator. Okay, so I'm just going to, now I'm going to take the antiderivative. And we're trying to get both sides from the derivative up to the function level. So this extends the problem a bit because we're having to take the antiderivative on both sides of the equation. Okay, so what does the integral of y become? Yes, y squared over 2. And then 2x becomes what? Yeah, 2x squared over 2. Now both sides produces a plus c, but we're just going to group all the plus c's together and put it on the right side.
Wait, so you only take the integral of the first term?
We take the integral of both terms. So the y becomes y squared over 2, and the 2x becomes 2x squared over 2.
Yeah, but what about the dy dx?
Okay, the dy dx's are just part of the notation, right?
Okay.
Before, if I take the integral of 2x dx, the dx drops out, and I'm just left with x squared over 2.
Okay.
Same thing here, y dy, the dy drops out, I'm just left with dy squared over 2. So the integral and dy are just notations. When you take the antiderivative, those notations drop out.
You have to leave as 2x over 2.
Yeah, we can do a little bit of cleanup. We can make it y squared over 2 is equal to x squared plus c. Okay, there's one more thing that we can do. Eventually, we're going to solve for y, but for now, let's just get y squared by itself. To get y squared by itself, I can multiply the entire equation by what? By 2. Now, 2 times c will give you 2c, but c will absorb any constant or coefficient into it. So 2 times c is still a constant. So we just normally just have it call it a plus c. Okay, so we start with the easiest example, and then we're going to kind of add to it. But that's the basic process. We get the dependent variables together, get the independent variables together, take the antiderivative, and then try to solve for y. In this case, I know we didn't quite solve for y, but we'll leave this as y squared. Okay, number 2. I'm going to cross multiply, but I'm going to, just so I can see all my numerator denominator, I'm going to rewrite it and put it over 1. Oh, and whenever they give you a different equation with parentheses already set up in the problem, they are meant to help you. Okay, so usually you try not to expand out, because the reason why the parentheses is there is to kind of help you separate the variables a little bit easier. So if you undo that parentheses, it's going to make it harder to get back. So I know typically we like to expand, but for differential equations, they are there to kind of help you out a bit. Okay, so I'm going to cross multiply here. Again, cross multiplying will not or may not separate your variables, but it will get your dy dx's locked in their right positions. Okay, and then we can decide, do we need to move the x's and y's around? Okay, so the whole purpose of cross multiplying is that first it gets rid of your denominator, and second, it gets your dy dx's in their right spot. So we know that we're not gonna have to move those. We're gonna move everything around it if we want to move things. We got to ask ourselves now, do we have full separation? Are all the y's and x's grouped on together on the correct side? Okay, something's out of place here. What's out of place? The 1 plus y. So we have to move the y, but that y is attached to the 1. So the parentheses is there to kind of help students identify, okay, I got to move this whole thing over. So if I want to move this over, I got to do what? I got to divide it. Yeah. So I got to divide it, which means that my y is going to be in the denominator, which is okay. Okay. We do have rules that can handle y's in the denominator. We just don't want our dy dx's in the denominator. Then everything is kind of misplaced. So I'll divide both sides by 1 plus y. And we should have full separation now. Let's take a look. Are all the y's together? Are all the x's together? Yes, okay. So the right side is easy. That's just power rule. But this side, we got to do a little bit of what? A little bit of U substitution. But this is simple enough where if you want to skip U substitution and jump to natural log, you can do it. But I'm just going to show the work in case you want to see it. So if I make my substitution here, integral of 1 over u du becomes natural log absolute value of u, which becomes natural log absolute value of 1 plus y. Okay, so if you're comfortable enough, you can jump from here to here, knowing that your 1 plus y won't produce any coefficient. It's just my u value there. Okay, so my left side becomes natural log absolute value of 1 plus y equals, what is the right side?
X squared.
Yeah,
Plus c.
1 x squared plus c. Okay, I want to solve for y, but my y is stuck inside the natural log. Right. So we want to undo this natural log away from this expression. The way we can do it is I'm going to involve the inverse. I know that e and natural log have a way of canceling each other out. So I'm going to introduce base e into the problem. I'm going to exponentiate both sides, raise both sides up as exponents. And the whole purpose is so that we can get that e and natural log to cancel out, force that 1 plus y, or that we can get closer towards solving for y. So whatever I do to one side, I can do it to the other side as well. E and natural log cancels out. I'm left with absolute value of 1 plus y is equal to. Now this is e to the x squared over 2 plus c. Okay. Sorry, I should have provided more room here. I'm going to bleed into number 3 a bit. Now, we're going to use some exponent properties here because if I have a base raised to the sum of exponents, I can break that into the product of bases. So absolute value of 1 plus y is equal to e to the x squared over 2 times e to the c. Do we all see how we use the properties here? So if I have a to the m plus n, I can break that down into a to the m times a to the n. Okay. Notice that this plus doesn't turn into a plus down here. It turns into multiplication. Right? If I multiply bases, I can add exponents. If I have the sum of exponents, I can break it down into the product of 2 bases. Right. Good so far. Okay, now e is a number. C is also a number. So e to the c is just one big what? It's just one big constant, but now it's being multiplied. So absolute value of 1 plus y is equal to e to the x squared over 2 times, I'm going to put a large c here. So now my c has turned into a coefficient instead of a number that I add just because I introduced this whole exponent. I'm going to go down here. Absolute value of 1 plus y is equal to c e to the x squared over 2. now that c is a coefficient, I'm going to bring it in front. I'm still trying to solve for y, but if I want to solve for y, I got to drop the absolute value. Absolute value means plus or minus on the other side because absolute value can hold both positive and negative values inside. So I can drop the absolute value, but if I do that, I need to balance it out with a plus or minus ce to the x squared over 2. Now we know that c is a constant, and the constant can be both what? Positive or negative. So I can just let that c kind of absorb both the plus or minus into it. Because I'm just looking for a general solution. So now my final step to solve for y, I can just subtract 1.
So whenever there's an absolute value, try to get it down to 1 term.
Yeah, try to get down to 1. This is my general solution for number 2. Maybe do a little more practice with this, but it is a little bit algebraically messy, but that's only going to happen if you have to undo a natural log that stores the y that you're trying to isolate by itself.
What about the negative?
Right. So of c can take both a positive and negative value. So we're just let c kind of absorb the plus or minus into it. Yeah, they can just take it all in. Yeah. Okay, let's look at number 3 here. Find a general solution, then find a particular solution. So general solution means there's a c in your answer, and then particular solution just means you're going to plug in the order pair, solve for c, and then update the equation with the c replaced. Okay. So first thing I like to do is I like to get my dy dx to show up. I think dy dx is it's the same thing as y prime, but dy dx is more visually helpful. It kind of helps us make sure that everything is in the right places. So I'm going to rewrite the problem here. 2x plus 3y dy dx equals 0. Okay, I'm going to rearrange until I can cross multiply here. I have 2 fractions equaling each other, so now I'm going to cross multiply. This will get my dy dx's in their right places. Okay, do we have full separation of variables now?
Yeah.
Yes. This is something that you don't have to do, but I like to do. Eventually, we're trying to solve for y. So anything that I can do to just start cleaning up the left side, it'll just make it less to do later on. So I'm just going to go ahead and move the 3 because I know the 3 has to eventually end up on the right side anyways. So the more I can tidy up, the less cleaning I'll have to do later. So I'll just move that 3 over. Get that left side as minimal as possible. And now I can move into my integral stage. Okay, dy dx's are in the numerator. That's good. X's are together. Y's are together. Any coefficients I can move to the right side, I did that already. So now simply power rule on both sides. Okay, integral of y dy becomes
Y squared.
Power rule on the right side as well. Negative 2/3 x squared over 2 plus c. Do some cleanup here. I'm also going to multiply a 2 through. Get that 2 to move over to the right side. Y squared is equal to negative 2 and 2 cancels out. I'm left with negative 2/3 x squared. Now 2 times c is still a constant, so I'm just going to put a plus c here. Okay, I'm going to call this my general solution because if I went any further, I would have plus or minus. I already have y pretty much by itself. I have a plus c here. So if I go any further, I'm going to be involving solving for c. So I'm going to call this my general solution. Now, my particular solution is where I'm going to involve order pairs and actually solve for c so that I can eventually update this equation with a numeric value for c. So I'm going to go to the top here, rewrite my general equation. I'm going to plug in my order pair here. So 1 gets inserted for x, -2 gets inserted for y. And now we're just solving for c, because once we solve for c, we'll come back to this equation and replace that c with the number that we find. So 4 plus 2/3 is the same thing as 12/3 plus 2/3. So that's 14/3 is c. So now I'm going to go back and I'm going to rewrite the equation with the c updated.
For the general solution, like see like y squared over 2 and you multiply it. If you multiply that c by 2, the constant would be 2. So like how do you
Right,
change
but-
this, right?
But remember, c can handle any number. So 2 times c is still a constant. So we'll just group any constant as just as a c.
Yeah, but when you plug in the point, the c value is gonna like change.
You're right. The c value will change, but it will always adapt itself, because if I find the c value here, it may be different than the c value there. But eventually, when I solve for y, that 2 is eventually going to update itself within the equation, right? So, but you're right. Depending on where you solve for c, we may get different c values, in our initial setup. But then by the time we clean up to solve for y, we should all be in agreement. Okay, are we good so far? Getting that c value and then updating the general to a specific solution. Now, there's one more thing that we can do, and with the general solution, we're trying to get it down to a function. So to get to a function, we can't have that y squared there. So how do we undo that y squared? Take the square root. Now, if you take the square root, what's going to pop up on the right side? A plus or minus. Now, these are two separate equations here. And these are two separate functions, but only one function can we use, because we're trying to find the function that will go through this order pair 1, -2. So which function can store this order pair? If I plug in 1, what's the only function that can produce a -2 for me? Yeah. You see that a square root can never produce a negative, but then if there's a negative outside the square root, then if I plug in 1, this will give me √4, and √4 is 2, and that negative is going to come into play. So if ever you're deciding between a positive or negative square root, look at the y value. If your y value is positive, it's got to be it's got to be positive square root to produce a positive value for you. If the y value is negative, then you know that you're going to pick the negative square root. But not every equation will have a plus or minus square root. But if you do have a plus or minus square root, you know that you can easily make the decision by looking at the y value of your order pair. It'll always match the sign of your order pair of your point. Okay, let's see if we can get through number 4 and 5 on page 2. Okay, find a general solution for y prime equals 6 cosine pi x. Again, my first thing is I like to get my y prime to be more descriptive, so I'm going to write it as y dy dx. And I like to cross multiply just so I can get my dy and dx's in their right places. Okay. Does everything look good for our separation of variables? Yeah. dy dx's are in the numerator. That's good. Your y's are together. Your x's are together. Again, it's okay to have x's and y's in the denominator, but we don't want dy dx's in the denominator. All right, we're ready to take our integral here. Left side is easy power rule. The right side here, we got to go through a little bit of what?
So
Yeah, a little bit of u substitution. So your u value is pi x. Now, just to a bit of a shortcut here, whenever you have a linear u value, the coefficient that's going to be produced is always the reciprocal. It's always going to be like 1 over pi. So it's kind of like chain rule, but opposite. But if you don't want to do that shortcut, you're more than welcome to just go through your derivative process there. But just want to offer a shortcut if you feel comfortable taking that job. So after u substitution, and I replaced dx with du over pi, I pushed out my coefficients here, 6 over pi, integral cosine u. This matches with my rule perfectly. Integral of cosine is sine. So now I'm going to take the integral on both sides here. Y squared over 2 is equal to 6 over pi sine of u. Replace the u back in terms of x. I'm going to do a little bit of cleanup before I plug in for c, just so I can just get rid of that 2 there. So I'll multiply everything through by 2. Get my equation as clean as possible before I work in my order pair. But ultimately, you can solve for c anytime. Right? You can solve for c at the very end, at the very beginning. We may have different c values, but once we solve for y, we should be in agreement with our c values. Okay, so I'm going to stop here and then just involve my order pair. Before my square root shows up, it just feels easier to save the square root for later. So I'm going to plug in my order pair now, solve for c, then update my equation, then I can get y by itself. So this is convenient because sine of pi is equal to what?
0.
0. So that's going to wipe this whole thing out. C is equal to 4. So here's my updated equation. Okay, I'm trying to solve for y here, so I'm going to have to take the what on both sides. Square root. There's 2 potential solutions that show up, but I'm only going to choose one of them. Which one am I choosing? The positive or the negative?
Positive.
Because my order pair is 2. 1, 2, right? The only chance I can plug in a 1 and get a 2 in return is if my square root is positive. So if I look at the y value of my order pair, that's going to help guide me which one I'm going to choose. Okay, number 5. Y prime equals x plus 1 over y. Let me get that dy dx to show up. Parentheses are there to help you. We don't want to lose those parentheses. Okay, cross multiply. Okay, at least my dy dx's are in their right places, right? We're not going to move them. They're already where they're supposed to be. Do you see anything out of place?
Why?
The y. So we got to do what with it?
Divide.
Divide it. Now, if you divide it, make sure you leave it in the denominator. Don't divide it and put it in the numerator, right? Algebraically, that's not correct. So, my AB students in the past, they feel uncomfortable with the y in the denominator, so they end up moving that y up to the top, but then that changes the problem, right? We do have a rule that can handle the y in the denominator, so we can leave it there. Okay, right side, we can do power rule for both these terms. This one is just what?
Natural log after.
Yeah, no need for use substitution. That's going to be an easy setup, but the cleanup is going to require a bit more effort here. Right, power rule for both. X becomes x squared over 2. 1 becomes x, and then there's a plus c. Okay, I want to solve for y, but y is stuck inside the natural log. What can we do to get that natural log to go away? Involve the inverse. We know e and natural log have a nice canceling out relationship there. So I can cancel out e and natural log. Absolute value of y is going to stay. Now, I can split all this up, but I'm going to split this up strategically here. I'm going to leave the variables together and separate the c, the constant, away from my variable, because I know that if I can get e to the c by itself, then remember, this is all sitting up in the exponent here. I'm just kind of rearranging it. I know I can replace e to the c with just what? One big C that's being multiplied, right? Drop the absolute value. Plus or minus c can just be replaced with just c.
I like skip the plus or minus.
Yeah, you can. Yep, yep. Okay, let's spend some time reviewing, going through some of the test review problems. Okay, so your homework is just 7.1. The keys on the website, page 25. Yeah, it's just 1 through 4. And then we'll say 7.2 for tomorrow. Okay, okay, so test review packet. Let's look at page 7. There's another Riemann-Sums problem here. Okay, so important key point here. Anytime you're applying or approximating a calculus process, either a derivative or integral, your units of measure will change. Okay. Okay, so let's look at number one here. Hot water is dripping through a coffee maker, filling a large cup with water. Sorry, a large cup with coffee. The rate that water in the cup is at time t is changing, is given by a differential function c of t, where t is measured in minutes. Select values of c of t measured in ounces per minute are given in the table above. So here at 0 minutes, there's no water that's been added yet. So ounces per, the rate is 0 ounces per minute. 1 minute in, the rate is 5.1 ounces per minute. So it starts off at a pretty fast rate, right? Coming out at a faster rate than later. Then it slows down. 3 minutes in, it's gonna the drip is going to decrease to 4.2 ounces per minute. Then by the time we get to 9 minutes, it's going to be a lot less coming out at that 9th minute, right? Only 1.2 ounces per minute, and it picks up a little bit at the 10-minute mark, right? So interpret the meaning of C prime of 6 and indicate the units of measure. So C prime of 6 is, okay, this is a rate of change of this. So what's the units going to be here? But remember, this is C prime here. So ounces per minute squared, right? Ounces per minute. So C prime of 6 tells us how fast the rate of water added is changing. So anytime we're talking about a rate of a rate, you don't want to say rate of a rate, and also you don't want to say acceleration, right? Because that doesn't fit the context of this problem. So you want to say the rate is changing. So you want to indicate those two components to indicate that you are talking about the rate of this particular rate. Okay. And also we know our units is going to be ounces per minute squared. So now let's approximate the value of C prime of 6. Just find the slope, right? Does it matter which order pairs we choose? As long as we're close, right? So you can use the 3 and 6, you can choose the 6 and 9, you even get away with the 3 and 9. Okay, I'm going to choose these two here, but you don't have to. So that means there's going to be a variation of answers that can be accepted for this problem. Okay, so the rate that hot water is being added at the 6-minute mark is changing at negative 0.7, or is decreasing. The rate that water is being added is decreasing by 0.7 ounces per minute squared. So that means it's slowing down, right? That from the 5th to 6th minute, or between at that 6-minute mark, we can expect that the rate to be decreasing, right? It's not coming out as fast as before. Okay, interpret the meaning of the integral from 1 to 10 of lowercase c of t and indicate the units of measure. Okay, Now, we know that if I take the integral, my ounces per minute will turn into what?
Ounces.
Because I'm multiplying these together, right? Integral, I'm multiplying here. But to help us see what this is really telling us, this is telling us this, right? Because if I were to work through this using integral notation, lowercase c becomes uppercase c. And uppercase c indicates the amount of coffee in the cup at 10 minutes, right? Minus c of 1. So the integral from 1 to 10 is the change or the amount of water added to the cup between the first and 10th minute, right? It doesn't mean that this means the amount of water in the cup. It's the change in the amount, right? So if we start off with 5 ounces and we end up with 15 ounces, then the amount added between the first 10 minutes is going to be 10 ounces. So this represents
Accumulation. Right.
I'm sorry?
I can also say like accumulation.
It is accumulation of the rate, but ultimately this is going to end up being the amount added to the coffee cup between the first and 10th minute.
Okay.
Right, in terms of ounces. Okay, so now let's get to the Riemann sums portion of it. Now let's approximate how much water or how much coffee has been added to the cup using 2 middle rectangles. So 2 middle rectangles from 1 to 10. A little bit of trial and error. I can understand that 1 to 6 can be one region, and then 6 to 10 can be the other region, right? Okay, what's the width of my first rectangle? 6 minus 1 is 5. Okay, what's the width of my second rectangle? 10 minus 6 is 4, right? And then the height I want to choose for my rectangles is 4.2 for the first and 1.2 for the second. Right? Don't do any type of averages. You're just picking out whatever y value that lands between your interval. That's the one you're going to choose.
Why are you skipping the 0 at the start?
Because we're only going from 1 to 10.
Oh,
Right.
If it would ask you to do a middle rectangle and it was only like 2 boxes instead of 3.
Right, good question. You're never going to have that situation. If it's a Riemann sums problem, they will always make sure that there's an odd number of intervals so that they can always pick out one. Yeah, so I've never seen a problem on the AP exam where they're asking you to find the average. There's always going to be one for you to find. Okay. Okay. Remember, if you're doing a calculus procedure on an expression, your units will always change. Either you're going to add another rate or you're going to remove the rate. Right. So here, my ounces per minute times time, right? I'm multiplying 2 units together. I'm going to get a different unit than when I started. Okay, find the average rate of water being added. So this is rate of water being added. So if I want to find the average value, then I can use average value theorem, right? So we can pull the value that we found from part D. So we have ounces divided by minutes. And we're back to ounces per minute. Okay, we can do some more practice tomorrow, but I will have a help session tomorrow morning and Thursday morning. I'll send out a reminder. Your homework tonight is 7.1 AP practice 1 through 4. Tomorrow we'll do a little bit more with differential equations, but then we'll use the second half to do more review. All right, come get your phones.
I get it. I think that's just like one day out break where you know that.
Good job. Yeah, over to society.
Yeah.
So why did you do, this minus this minus this?
Because you can, yeah, you can do this minus this. So your answer may be different, but they'll be acceptable.
We need to get 5 months. Is there gonna be summation on the test or?